Welcome to another Newton's method example. So in this example, we are going to use Newton's method to find the root of f of x equals x to the fourth minus 3x cubed plus 3. That falls between 2 and 3, and we should specify that this is, let's go to 3 decimal places again. So just a quick note, if we graphed this function, we would find that the root that falls between 2 and 3 is pretty close to 3. So just a note, if you graph the function, the root between 2 and 3 is close to 3. It's close to x equals 3. So we will go ahead and set x1 equal to 3. If you don't have a graph, you could pick either end to start, or you could start at, say, 2.5, start in the middle of the interval. So we'll set x1 to be equal to 3. We are also going to need f of x and f prime of x for our own reference. So off to the side, and let's just keep in mind, f of x is x to the fourth minus 3x cubed plus 3, and f prime of x is 4x cubed minus 9x squared. So if I want to find x2, we have that x2 is x1 minus f of x1 divided by f prime of x1. And so again, x1 is equal to 3. And we have f of x1 is f of 3 which I believe is just 3. And f prime of x1 is f prime of 3. Which I'm going to plug into a calculator. So if we plug that into our calculator, I wind up getting 27. And so we have that x2 is equal to 3 minus 3 over 27. And if we do that, we have 2.8, the 8 repeating. So here we now have x3 is equal to x2 minus f of x2 divided by f prime of x2. X2 was 2.8 repeating. F of x2 is therefore f of 2.8 repeating. And f prime of x2 is f prime evaluated at 2.8 repeating. So if we plug those into our calculator, we wind up getting f of x2 is 0.321, and f prime at x2 is 21.327. So we have x3 is equal to 2.8 repeating minus 0.321 dot 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 divided by 21.327 dot dot dot. And if I plug that into my calculator, we have 2.873. So we're no longer 2.888. Our digits have changed. So now we're going to go ahead and find x4. So x4, we are looking at x3 minus f of x3 divided by f prime evaluated at x3. Again, x3 was 2.873 dot dot dot. Oops. Then we have f of x3. We're looking at f of 2.873, which is 0.0054. And then f prime of x3, we are looking at f prime of 2.873 dot dot dot. And that winds up being 20.608 dot dot dot. And so if we find x4, we have our x3, 2.873 minus 0.0054 divided by 20.608. And this winds up giving us 2.8735 dot dot dot. So once again, our x3 and x4 agree on those first 3 decimal places, so we can go ahead and stop. So note x3 is 2.873 something, and x4 is 2.873 something. These agree for the first 3 decimal places. If they asked to approximate to 4 decimal places, we would have to keep going until they agreed for the first 4, right? But we just needed the first 3. These agree. And so what we get is our approximate root is x equals 2.873. So Newton's method, when we use it, can be much faster than the bisection method, because just the way it works, when Newton's method does work, it tends to shoot us in towards the root much faster when we do these tangent line approximations. And again, that's because when we're close to, when we zoom in, our tangent line approximation looks a lot like our function. So it makes sense that as we use our tangent line, it should get us closer and closer and closer into that root. In the next video, we'll see ways in which Newton's method can fail us. So these 2 problems, we did Newton's method very quickly, zeroed in on a specific point. But sometimes something can go wrong. So again, in the next video, we'll see where Newton's method can go wrong.